Welcome back to the afternoon session. For the first talk, we have Iñaki from Durham, who's going to tell us some aspects of symmetry descent.
Thank you very much. First of all, thanks to the organizers for putting together such an interesting conference and for giving me the chance to speak. I want to discuss some work I did with Sagar, who was my PhD student, but is now a postdoc in Tokyo. And it's about something we call symmetry descent, which I will try to explain in the talk and motivate the reason for the name. So this is going to be a talk about theory, but if you're not a string theory, you don't need to worry. For me, string theory is going to be in this talk some sort of black box that takes geometries and constructs quantum field theories out of them. So I'm going to call the geometries that I will be discussing X, for example, and these are typically singular. I will describe this in more detail in a second. Manifolds, and out of such a singular manifold, you can construct a quantum field theory. And there's some rules that you can learn and go through the motions. If you learn this rule, you can call yourself a geometric engineer. What we have learned in the last few years is that if you want to think about quantum field theories, as usual, this is from a long time ago, the first set of data you want to learn about quantum field theory is the symmetries of the theory. And, oops, to start the timer. And the object that encodes the symmetries of the theory in a very neat way is the symmetry theory. I'm going to call that symTx. And there have been many works on this. Here's a selection, and apologies if I miss some important works. What we found in the last few years is that it's significantly easier, and at least in the context of string theory, to understand the symmetries of a theory, understood as this topological field theory, symTx, than the theory itself. Tx can be very complicated, but the symmetries of the theory turn out to be much easier to understand. What I will do today is to review some recent results, which are, the way I view them, some step in a longer-term program, how to do this procedure systematically, how, given a geometry X, construct symTx without knowing Tx. So we are familiar, and we have heard talks in this conference, that if you have a theory, you have a Lagrangian, for example, in principle it's possible, but typically very subtle, to find the symmetries, and in this way you can reconstruct the symmetry theory. If you're a string theorist, if you're a geometric engineer in particular, having a Lagrangian is a luxury that you typically don't have. So, in fact, it's more the exception than the rule. Typically, we can construct a lot of geometries for which we don't know how to construct a Lagrangian that describes the law of energy physics, but we believe that there's a quantum field theory and we know things out of this quantum field theory. Typically, what we know is something about the topology of X, and sometimes we know the metric, if we are lucky. It is precisely in the cases that we don't know a Lagrangian, the cases that we don't have a standard approach, that the information that you get from the geometry approach that I'm going to describe is most valuable. If you don't have a Lagrangian, at least you can try to get something out of the symmetries and anomalies. So what do you need to know from this talk? Not much, luckily. The first thing is that I will be talking about different versions of string theory, M theory, type 2B, type 2A. These are all secretly the same. So think of one string theory, this one black box that given geometry gives you quantum field theory. And the basic picture you have in mind is something like the following. So you have a product of two spaces. One of them is the singular manifold X. The thing that's the input to this map symTx. X for me in this talk is going to be some sort of cone, which is singular. And it has a base, which is going to be called B, or later on talk perhaps L. Times, so this is just the direct product of two spaces, some space M, which is where the field theory will live. So the intuition you should have when you see this kind of picture is that the string theory makes something interesting happen at the tip of this cone, at the singular point. And because you have the direct product, the interesting things are happening in the point times M, so you get some interesting quantum field theory effectively living on M. So that's the name of the game. The details of how this happens are not going to be essential for this talk. For reasons of analytic control, sometimes you want to break this to make the theory more interesting, but in this talk, I'm going to take the simplest sort of X's that I can consider. I'm going to take X to be non-compact to the coupled gravity. Ibu gave a great talk yesterday about what happens if you start coupling gravity. And to make our life simpler, I will assume that X is a real cone over some base. There's no real reason for this, but it makes things easier. And in order for the field theory to be supersymmetric, to maintain some degree of control on the configuration, we assume that X has some special properties. For example, I will assume here that it's a cavia. So whenever you have this kind of configuration, this cone, you have to tell me what happens at infinity. So in particular, in string theory, there are going to be some supergravity fields, and you have to tell me what happens at in the infinity, which is in this case, assuming that M is compact, infinity in X, so basically the base of the cone. So you have to tell me what the fields do at infinity, which is a copy of B times M. If we go back to this picture, infinity is going to be somewhere here. It's going to be a copy of B times M. So this is what I have to tell you if we want to define the theory properly. And to connect with some things we know already, in field theory, this boundary behavior of the supergravity fields, the boundary fluxes, disappear as background fluxes for the higher form symmetries. So we can start connecting these two languages. So the way this works in string theory is something that I will connect in a second to the SymTFT picture that we all like. We do this by giving a state in the Hilbert space associated to this submanifold of a space-time. And this is, of course, a complicated thing to do. String theory is a complicated theory. But the sort of crucial statement for many things is a phenomenon that was observed many years ago by Moore and Freemoore and Segal, which is that the fluxes in supergravity don't commute. The problem of giving boundary conditions is actually quite involved. As it happens, it's involved in precisely the right way to reproduce many of the things that we know about quantum field theory. So that's the picture. We have this cone and some high codimension locus. You have some interacting excitations. And you want to understand the behavior of these excitations as a quantum field theory, and for that you have to give me the behavior at infinity. So in the language of relative theory, we have something like a QFT on a singularity, living at the tip of the cone, which is relative to the string theory bulk. So we make it relative with respect to all bulk, not just a dimension plus one space, as we are used in the SymTFT, but something that could be many more dimensions. And you have to do this because the path integral of the quantum field theory, we don't know how to compute it, but one thing that we know we need to specify is the boundary values at infinity, and you need to specify those, and they give different answers in a way that we understand. So I emphasize that this happens even in the deep IR limit. So even if you decouple the degrees of freedom in the quantum field theory from gravity at 3 level, you still have to give me this information. So the coupling is not perfect. You don't have just the theory of the singularity, you still have to tell me a little bit more data about the space it lives in. Okay, so in general this gives some relative version, but the space in which this theory lives has many more dimensions than the space where the quantum field theory lives. So string theory is 10 or 11 dimensional, and maybe you're engineering a 4-dimensional theory, so have 6 dimensions of difference. We have heard in many talks already that the SymTFT is a good way of thinking out the symmetries of some quantum field theory. So I would like to connect the description, the geometric description I just sketched, to the SymTFT picture that I have here. In the SymTFT, the bulk has one higher dimension. So how you do this? Well, if you look through the details of this paper, what you see is that you're doing a quantization basically radially. So the picture is more like this. You have sort of deformed the cone into a cigar. I don't want you to take this particularly seriously. This is just the motivation for the more precise mathematical technique I'm going to explain. But just looking at this picture, at this sketch, it seems natural to think that if you take this sort of cylinder and you make the base very small, you're going to end up with some picture in which you have a field theory on some space-time times a semi-infinite interval, which is the radial direction on the cone. And this is starting to look more like the SymTFT picture, in which you have some gapless degrees of freedom here, and you have to give me some data at infinity, which introduces no extra degrees of freedom, but it's important for specifying the global form. Okay? So in the SymTFT picture, you should think of the origin of the cone as the gapless boundary, and the infinity in the cone, far away, this should be the gapped boundary. Essentially, this is what should be happening. And in a paper with Fabio, Federico, Sagar, and Sakura, and also important previous work by Federico, Ibu and collaborators, and Miriam, we sort of put this into firmer footing. And I'm going to describe that in a second, but before, let me point out some small thing. There's going to be a bit of a theme in this talk. So the picture here is going to be that the quantum field theory living at the singularity is connected to the SIM-TFT. So I want you to think of this sort of picture as something like anomaly in flow. Many old papers in the literature in the string theory were talking about anomaly in flow in this sense, and our discussion is very connected to that. But in this case, we can think of the full set of symmetries, not just the particular global form with its anomalies, but the whole set of symmetries, the whole SIM-TFT, in the language of inflow. So much of what I'm going to say later is going to try to make the symmetry inflow words more come to life. Anyway. So what was the idea? What do you do? Well, you make this reduction. Let me give you an example. Imagine that you have some theory. In this case, we're looking at a 5-dimensional conformal field theory coming from M theory. So M theory is an 11-dimensional theory. We put it in a cone which is 6-dimensional. So the tip has codimension 6. It's going to be a 5-dimensional quantum field theory. This 5-dimensional quantum field theory has a SIM-TFT which is 6-dimensional. So this is the object that I'm describing here. And this SIM-TFT can be written in terms of a BF theory, so it's B wedge DC. So some sort of BF theory, discrete gauge theory, and then some coupling that encodes anomalies. In this case, it was a B cubed. And this is the result that you expect from field theory analysis in the case that you have a Lagrangian. So we explain how this appears in a string theory. This first term comes from flux non-commutativity again. This is a very crucial phenomenon in this whole game. And the anomaly term arises, simple cases, at least from reduction, so in this case in particular, from reduction of the string theory action. For instance, in M theory, you have a term that looks like this too. So in this case, let me focus on C3, wedge G4, wedge G4. This is a sort of Chern-Simons term with more indices. If you take the Chern-Simons term and you integrate on the base of the cone, you get precisely this coupling. The details are not going to be very important. But this is what you get. You do the integral of this Chern-Simons term and you end up with this coupling, which is what you expected. Now, this was, to me, very convincing that the picture is in the right track, but there are a couple of shortcomings that I want to try to resolve in this talk. I won't be able to do it completely, but I'll make some progress. Which is the following. In computing this action, we are computing this BC term, B wedge DC, using the flux non-commutativity, and the B cube term we are computing by doing an integral. Okay, so these are two techniques for computing different terms in the Lagrangian. That's not something that you should. I didn't find it particularly beautiful. I would like to have one procedure that gives me everything. I'll explain in a second why this is hard, why we couldn't do it at the time, everything at once, and we still can. We still cannot. But anyway, that's the issue. We use two techniques for computing two couplings. Both separately are convincing, but of course the interesting thing will be to try to have a unified description. So what I will do is I will try to understand this coupling, the one that we argued using flux non-commutativity, using dimensional reduction. So I will try to think of the whole thing as coming from dimensional reduction. There's an alternative approach that you can take, for example, papers by Michele and collaborators, in which you try to understand the anomaly term using a language that is close to this one. That's also a unified approach, and that's also interesting. Eventually, we'll want to unify everything, but I don't think we're still quite there. So what is the basic abstraction? Why didn't we just do the reduction, right? The basic problem is that if you look at the BF sector, the B wedge DC, you think out the electric degrees of freedom of M theory. In M theory, you have a three-form connection, so something like a connection like an A, but with three indices. I call it C3. And B comes from C3, essentially. The details, again, not so important. But C comes from the magnetic degrees of freedom. So if you dualize in 11-dimension C3 form, or you get a G4, which is DC3, you get a dual G7, a star of G4, and the connection for G7 is going to be C6. So you have a 6 form, which is the magnetic field. And C comes from the magnetic degrees of freedom. So if you want to understand this coupling from some sort of reaction, it's definitely possible. You can do it. But you need to work democratically. You need a formulation of 11-dimensional supergravity in which C3 and C6 appear at the same time. It's not a standard kind of thing we do. We typically pick the electric degrees of freedom and work there, or the magnetic bonds and work there. But here we want to work with both. This problem is, of course, more or less the same problem as trying to describe a self-dual field. And in different variants of this problem, it's literally a problem of trying to describe a self-dual field. In this case, you can think of the self-dual field as the pair C3, C6. So the pair itself is self-dual. And you want to write a theory in which you have this self-dual field. This is, of course, a very, very well-studied, subtle but well-studied problems, and there are many solutions. And we could approach, I think, this problem in some of these ways. But the point of view that we found most illuminating was the following one. So let me sort of study a baby version of this problem. When you in this case, we consider generalized Maxwell. So remember that M theory has these extra Chern-Simons couplings, which are a little bit troublesome. But I'm going to forget about those and just think of M theory as a generalized Maxwell. That means a theory with a p-form connection, AP, and an action, which is the field strength of AP, so Fp plus 1, wedge star Fp plus 1. So the standard Maxwell, only with p-forms instead of 1 forms. Right, so I mentioned here it's often useful to think of this as being coupled to background fields, so the corresponding symmetries. Of course, we know how to do that, and it's very natural from the point of view I'm going to explain, but here I'm setting those to 0. Okay, so you can write this theory, or if you prefer, in this particular case of the abelian theory, this is a free theory, you can dualize exactly. We know how to do that. And this can be described equivalently in terms of the magnetic connection, which in this case is a D minus P minus 2 form. So you want a formulation that sees both A and AD. So the formulation that we found most useful, not necessarily the only one that could have worked, but the one that we could make progress with, we worked in a formulation that was, well, we made use of an observation of that was in this paper by García Etxebarria and Yonekura. Although the results connect very nicely to some previous work by Maldacena, Moore, and Seiber. So we want to think of the generalized Maxwell theory I just described as a theory of edge modes of some theory in 1 dimension higher. And this theory in 1 dimension higher turns out to be Maxwell BF. So what's Maxwell BF? Well, you start with a BF theory of the type that I have been talking about, 2 pi I k B which star DC, and you add kinetic terms for B and C. Very mild modification. Now, one thing to keep in mind, because it's easy to lose track which thing is which, you should think of this boundary theory as a string theory itself, the thing that when you reduce, you get the sim TFT. And I'm going one level higher. So I'm going one level higher than string theory. So if I started here with 11-dimensional supergravity, M theory, this would be 12-dimensional. And the way to think of these fields that live here, B and C, is as if the field strengths I had for A and A dual in here, so the F and F dual, became dynamical fields in here, connections for some higher boundary. So the fields have gained a leg, if you want. I'm going to Maxwell BC. Maxwell BF. So away from the boundary, this theory doesn't, this modification and in the kinetic terms doesn't do anything to the BF theory. The B and C fields have a mass, and in the limit in which you send E and M to infinity, you recover a standard BF theory. So this is something that really doesn't do much in the bulk. But it was shown in this paper by García Etxebarria and Yonekura that there's a difference with respect to standard BF theory, and that is that close to the boundary, there are classical solutions of the Maxwell Chern-Simons theory that localize exponentially close to the boundary and describe, in their case, a self-dual field. In the case I'm talking about, we are describing Maxwell theory. So the picture is like this. We have the bulk In most of the bulk, we have a BF theory, but there's a mode exponentially localized close to the boundary, and the dynamics of this mode is the dynamics of the Maxwell field. So one of these P-form connections. So to show details, we take an ansatz close to the boundary in which the field strength for B looks of this form, something that is exponentially localized. I'm taking the tau coordinate to be infinite in the negative side. So it goes from -infinity to 0, and things are localized at 0. So this is exponentially localized around 0. And we have these functions f and g, which are functions of the boundary coordinates. So if you put these B and C inside the Maxwell BF equations of motion, this is a straightforward exercise, you will see that F and G have to be flat, and alpha has to be equal to beta, and the most important bit is this one, star of F is equal to G. So if you look at all these equations together, they tell you that dF is equal to d of star of F equal to 0, and these are precisely Maxwell's equations for F, the absence of sources. So this is a purely classical analysis, a beautiful result of Tachikawa and collaborators, that these are these classical modes there that do the... Yeah.
I'm not sure I understand this point. I mean, even if you just start from the BF theory, it's still true that you have edge modes which are generalized Maxwell field at the boundary.
Well, you have to modify, perhaps you're thinking on the modification of the boundary condition.
Yes.
Yeah, I won't comment on that in a second.
Okay.
Yeah. Here I'm not modifying anything, I'm not putting a boundary term, but I will see it arise in a second. All right, so you get Maxwell's equations in this really nice way. And now you have to specify the boundary conditions. I'm going to choose purely Dirichlet boundary conditions, in particular B equal to C equal to 0, and tau equal to 0. And I emphasize if you want to turn on background fields, now it's easy, just choose different values here, as you might imagine. But I'm not going to need to do that here. And this does not kill the space of solutions. You still have all the solutions you wrote. Basically, you take a B of this form. You will see that at tau equal to 0, this thing becomes 0, and this is still exponentially localized. Well, as I say, it's exponentially localized, except for the fact that as you go to very negative taus, you get that B is equal to F. Now, in the BF theory, in the bulk, B and C are not 0, but they have to be flat. A different way of saying that is that they have to be pure gauge. So one thing that's interesting from this point of view, and will connect to the boundary conditions you were talking about, is that you can think of the F and G that describe the Maxwell theory as being the pure gauge B and C as we approach the boundary. So in particular, if you think that F is D of A and G is D of A dual, these A and A dual are the gauge parameters. So if B is pure gauge, F is going to be D of lambda, the gauge parameter. So my connection in the boundary, the thing I tend to think of as the Maxwell field, is really the gauge parameter, the lambda, in which I'm transforming the B's. So what's happening in this kind of setting is that the gauge parameters, the B's and the C, are becoming alive, and they describe the Maxwell field. Of course, that's all fine because my boundary condition is not gauge invariant, so it's possible that the gauge transformations do something interesting, and in this case, they become Maxwell. So to connect with the previous results by Maldacena, Moore, and Seiber, you can take this limit, E goes to M to infinity. And here what I have done is I have sort of zoomed into the boundary and made the region close to the boundary large. And then I have taken this limit. So even if I'm very close to the boundary in a tubular neighborhood, if you like, my Maxwell solution is still exponentially localized. So that's the picture. I have a region, I've called it here near boundary, where the B and C are still pure gauge. And there's a very little region at the end of the boundary, where these things are actually not pure gauge anymore. They become interesting in the Maxwell field. But I can sort of forget about this region and reproduce the previous analysis if I impose that in the near boundary region, my B and C are pure gauge, everything has to happen here, and the gauge transformations behave as in Maxwell theory. So that's precisely what is achieved by adding this term you're asking about. Notice that this term, again, is not gauge invariant, but here we understand it in the sense that we have this non-gauge invariant boundary condition, B equal to C equal to 0, and in the effective description, we get a term that reproduces the dynamics. So I'm going to argue now, this was, it might seem a little bit abstract, but I will argue now that this is actually very useful for our goal, this goal of building a machine that, given geometry, gives us sym-TFTs. And here's the basic idea. It's something that was done or mentioned in a number of papers. Here's a selection. So here's the picture again. I want to integrate, whatever that means. On the base of B5, I want to give a meaning for this picture and obtain a TFT by integrating string theory on the base B5. Just for the purposes of this talk, let me simplify the problem a little bit. Let me imagine that my manifold M is just a point, so I'm going to forget about that. And I'm going to look at this kind of cigar geometries, four-dimensional cigars, where the base, I'm going to call it L, is a lens space. And what I want to show is how if you take Maxwell theory on a lens space like this one, you end up with a one-dimensional topological field theory of a very simple type, a discrete set in quantum mechanics. And this is just an example. Of course, in practice, you want to have some M's attached in here, but the gist of the physics can be seen already here. Okay, so what did I just argued that if I have a BF theory in this space with boundary, where the boundary is X times L, and I do a gauge transformation, the effective theory that describes the gauge transformations is Maxwell theory. So if I take this BF theory, gauge transform, and then integrate, I'm going to get the BF theory. So the sym-TFT that I'm after. Let's do that. I'm going to say some words here about how we did it, just because I think it's beautiful technology. I'm not going to explain it in detail. But we follow these ideas of Hopkins and Singer, or this goes back to Chiker and Simons really in this specific example, but Hopkins and Singer generalize to other cases of interest. And we are going to describe gauge fields by this kind of triplet. So it could be an integral cochain, a real cochain, and differential form. Again, the details are not super important. The thing I want to sort of advertise is that this technology is actually very useful in practice for the purposes here. So I want to, maybe I should say this more explicitly. I want to do an integral on L, which is a lens space, a space with non-trivial topology, of bundles which are topologically non-trivial. So speaking about Chern-Simons in topologically non-trivial spaces is difficult, as we all know. And this technology is a way of doing this in a controlled and systematic way. So you have many things that you're familiar with. There's a differential that squares to 0. There's a product, like the cap product. There's the fiber integration map that behaves like a fiber integration map. And there's a Stokes formula. So once you have established these facts, you can basically do the integrals. A U1 bundle with connection is represented by one of these sets. Set here means cocycle, so there's something as a differential cocycle. And gauge transformations, also global gauge transformations, so large gauge transformations are of this form. Anyway, there's technology for doing this. But the point I want to emphasize why we did this is that we want to work locally. We want to construct the Lagrangian density for the sym-TFT. And that requires, for us, working with non-gauge invariant fields. So we cannot work with something that some of you might be more familiar with, differential cohomology classes. We really want a connection here, because we want to talk about how things change when we do gauge transformations. And we want to do that keeping track of the topological data. So this formulation by Hopkins and Singer was very well tailored for this kind of program. So we want to work in a way that we can obtain Lagrangian density for the sym-TFT. And that's very important physically, because generically the thing you want to do is you want to put the sym-TFT in a space with boundary. And here I'm seeing the sym-TFT itself as living on the boundary of something. Of course, the boundary of a boundary is 0, unless you involve corners. So it would be much more challenging to do things if you couldn't work locally, but luckily we can. Okay, so here's the sketch of the argument. So we go one dimension higher. You can think of Maxwell as the H modes. So the BF theory, when you put hats on everything, meaning you walk into the Hopkins-Singer formalism, it looks like this. You impose the boundary condition I described. Everything is pure gauge. In this language, that's what it means. The BF theory itself is something which is not gauge invariant on spaces with boundary. So you can compute the gauge transformation. Here it is. It's something that localizes on the boundary, as we all know. BF theory in space with boundary has a gauge transformation that localizes on the boundary. And then if you do the integral, you get precisely what we obtain. It was a little bit quick, but hopefully won't surprise you that you can actually do an integral on a lens space using this technology. Okay, so this works very nicely. But once you have established that this direction of the arrows works, you can argue that there's a different way of going in this direction. First, you start with the BF theory, you integrate on L, and then you gauge transform. And that gives rise to what I'm going to call symmetry descent. So this H of integral of L, this is the effective action in this bulk. You do a gauge variation that gives you the exterior derivative of the Lagrangian density. So this is like in the standard anomaly descent, in the second step of anomaly descent. But here we see one step higher. So the SymTFT now lives here. So the SymTFT itself appears in this kind of descent-like formalism. Let me say very quickly, and then I conclude, that you can include couplings, at least some of the couplings, by complicating a little bit the formalism. So if you go to something called H-twisted K-theory differential cocycles, we could show in some cases that this still works. You can get some of the couplings, these anomalies, so not just the BF terms. Unfortunately, we cannot get everything that we know to be true. So in M theory, there's a coupling that when you go to a bulk is G4 cubed. In my formalism, this will be connection times connection times connection. We don't quite have the formalism as far as I know to understand this. The same TFT is a fully extended TFT. We like this machine to give us a proper topological theory, not just dissection. Hopefully we can do that. You should include branes and non-abelian stacks. I'll leave that an exercise. Thank you.
I'm a bit confused which of your fields are dynamical and which are classical. In the standard geometric engineering, you get dynamical fields living in the singularity or the brain, and everything in the bulk is classical.
Yeah.
In the SIM EFT, they are dynamical. You need to separate the scale such that they become dynamical. So you need to take a special limit of what you're doing such that gravity is decoupled. The field that you would call the bulk remain dynamical. It's not clear to me to what extent you took such a limit.
Yeah. So the thing I obtained in the end was a gapped theory. It was a certain gauge theory that lives in the bulk. If I specify the boundary conditions at infinity of these gauge fields, I'm fixing the background fields for the QFT, but I'm not adding degrees of freedom.
The bulk is infinite?
The bulk is infinite, yeah. So if I have an interval, so an infinite interval in which I put a DFT.
You have to take a limit that the graviton in the bulk is not there.
Yeah.
Strictly speaking, this is not, the bulk is not a gap theory.
Yeah.
The graviton.
Yeah, no, you're completely.
Limit that the graviton is decoupled.
Sorry.
You need to take a limit that the graviton, which is gapless, is decoupled, and your other fields remain dynamical. Maybe you did it, but I missed it.
That's completely right. So that's the remark I made at some point, that this picture of integration should be taken a little bit as motivation of what I'm going to do. The structure I gave later in the talk, this one here, this formula here. This is a formula that I claim gives you the same TFT, but it's not a compactification formula. I'm not doing what you asked to be done, which is I'm not compactifying on the base of the cone, because I think that's a bit meaningless, right? It's not an actual cone that I'm making small in string theory, in that way making things...
But then, why are these dynamical fields? I would say that they are classical. I think what you will derive, if you took the limit you just described, what you found was the anomaly theory, which the invertible theory. So it's not the same TFT.
No, that's what I'm trying to emphasize. Yeah, I'm not doing that. I'm using this picture for motivation, for giving a prescription, which is this one. that engineers for me the same TFT. I don't think it can be done the motivation, strictly speaking, trying to do a compactification in a way that decouple gravity consistently and so on. I don't think that makes sense as it is. I think you can do it. But this formula here is a perfectly well-defined formula, relation between TFTs. So it just motivates this relation, but it doesn't justify it.
In the interest of time, let's save the discussions for coffee break. Thank the speaker again.
Okay.